Good day, grade 12 learners. Welcome to today's Technical Sciences lesson. My name is Musa Zulu. This lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. Grade 12, our knowledge area for the day today, we are doing electricity and magnetism. Paper 1 stuff. So we are going to paper 1 this time around, grade 12. And specifically, we are going to be looking at electrostatics. Okay. Later on, we'll be looking at electric circuits, but that's for the following week. But it's electrostatics and electric circuits. I like to combine them when I talk about them. But today, we'll be specifically looking at electrostatics. And specifically, when we are talking of electrostatics, we'll be talking of capacitors. Okay. You'd remember that we looked at electrostatics last year. We looked at Coulomb's law, we looked at electric field around the spherical charge, electric field around parallel plates, all of those things. And then last year, we also spoke of uses of electrostatics, where we were talking of defibrillators, we were talking of spray painting, we were talking of capacitors, right? With people that I was teaching last year, I even said, we will deal with this capacitor in more detail when we get to grade 12. And this is the time for us to do that grade 12. We're going to be looking at capacitors, looking at them in more details. How is it that electrostatics fit into capacitors and all of those things? So that is going to be our topic for the day, grade 12. So let's just get right into it there. Okay, so our objectives or lesson objectives for the day is that by the end of the lesson, we want to be able to define a capacitor. We want to be able that we can define a capacitor by the end of the lesson. We want to be able to define capacitance, and we want to know the difference between the two. So we must be able to know the difference between capacitor and the capacitance. Okay, and the capacitance. We must know that one is a device, the other one is a concept, it's an idea. Okay, so there must always be that distinction between the two, that when you're talking of a capacitor, you're talking of a device, a tangible thing, something that you can actually touch, something that you can place and take. Okay, but when you're talking of capacitance, the idea, it's the concept that we are going to look at. Okay, the concept of the device itself. So capacitor and capacitance, there's a difference between the two. So that whenever we are asked for capacitor, we know what is being asked, and whenever we are asked for capacitance, we know what is being asked, and we know the difference between the two. Okay, then from there, we are going to look at the functions of the capacitor, including the capacitance as well. Then we are going to calculate the capacitance of different capacitors using the potential difference V and the charge Q. Okay, so we're going to look at how can we calculate the capacitance of a capacitor if we know the potential difference V of voltage, okay, and the charge Q. Okay, then we'll also calculate the capacitance of different capacitors using the area of the plate and the distance between the plates of the capacitor. The distance between the plates of the capacitor. So there are two ways in which we're going to be trying to calculate the capacitance of the capacitor, the magnitude of the capacitance of the capacitor. Then from there, we'll then look at stating the factors that will affect the capacitance of the capacitor. To say what factors will affect or can affect the capacitance of the capacitor, and what are those factors and how can we state them. Then towards the end of the lesson there, we're just going to look at some examples of capacitors used in technology. So we'll look at some examples of capacitors and how those capacitors are used in technology. Okay, so those will be our objectives. Okay, so what is it that we are expected to know coming into this lesson, grade 12? Well, I've already spoken saying that we've done electrostatics at grade 11. We talked of Coulomb's law. We talked of charges. We spoke of electric field. Even though Coulomb's law is not that much needed here, but the knowledge of charges is very, very important, grade 11. But here, I'm going to need you to know of electric field. What is an electric field? We spoke of this in grade 11. Are you able to draw the electric field lines between two parallel plates. You would remember again, we drew electric field line between a spherical object, maybe for example, like this, and then we said there will be electric field lines around the object, and then we were speaking of the direction of the electric field lines to say in what direction will they be pointing. Are they pointing away from the charge, or are they pointing towards the charge? We also have that positive test charge thing that was telling us the direction. But we also had electric field lines between two parallel plates, which that knowledge will need to use it here. Let it come back to you so that you can get a better understanding of these capacitors. So drawing of electric field lines between two parallel plates, very, very important. Okay. Number 3, are you able to calculate the area of the square or a rectangle? Are you able to calculate the area of a square or a rectangle? But most importantly, a rectangle. Square, possible, but rare, this one, okay? This one can happen, it's possible, but it's rare. Most of the time, it's going to be rectangle because we're going to be talking of these parallel plates, and most of the time, we're not going to say always, but most of the time, they are going to take a what? A rectangular shape. They are going to take a rectangular shape, okay? Are you able to calculate the area? Again, grade 12, you would remember this is bringing us to some of the lessons that we had when we were talking about pressure, when we were talking about stress and strain, when we were talking about hydraulics, okay? This issue of being able to calculate the area is very, very important in the subject, especially when we are looking into paper 1, grade 12. You must be able to calculate the area. If you've been with us since then, by now you know that the issue of calculating area is very, very important to us. And immediately I speak of the issue of calculating into area, there comes another thing now that we spoke about before. Being able to convert between units. You must be able to convert between units of measurement. But this time around, it will be the unit of charge. Okay, where we are going to be speaking of units like millicoulombs. Okay, we will be talking of units like millicoulomb, very rare this one, but we will also be talking of units like, let me write that correctly, microcoulomb. We'll be talking of units like nanocoulomb. We're talking of units like picocoulomb. Are you able to convert from milli to micro to nano to pico? Do you remember those conversion factors that we were talking about? To say milli is times 10 to the power minus 3, micro times 10 to the power minus 6, nano times 10 to the power minus 9, and pico times 10 to the power negative 12. Those are the conversion factors that you need, especially for the charges here. Are you able to convert between the units of distance, where you'll be talking millimeters, maybe centimeters as well? Most of the time, we'll be talking millimeters and centimeters. Are you able to convert between those units? And are you also able to convert between the units of area? To say, are you able to go from the square centimeters to square meters? Are you able to go from square millimeters to square meters? Those things are some of the things that can actually help us. While the concept that we're going to be looking at is not a difficult concept, grade 12. So it's really not that difficult. It's easy to understand. You will see it's easy to grasp, it's easy to understand. It is easy to even expect questions that are going to be asked. You see, with this concept here, you can actually corner the examiner easily. There's a limit of questions that can actually be asked by the examiner in this concept. So these are the things that we would expect that you know, okay? And here is the assessment that I will try to use to sort of check whether people can do these things here. So the first one will be saying, define the term electric field. And number 2 says, draw the electric field lines between the following parallel plates. So you can just simply on your book there, just draw the 2 plates. This one is positively charged and this one is negatively charged, and quickly draw the field lines here between the plates. Want to see if you can still remember how those field lines should be actually drawn. Okay. Then number 3, calculate the area of a shape with a length 2 centimeters and a breadth of 4 centimeters, or width. This is also called width, okay? Width of 4 centimeters, okay? Right. And then the last one there is asking you to convert the following units to standard unit. Convert the following unit to standard unit or to SI unit. That will be 600 PC. What does this PC stand for? That's picocoulomb. Okay, that's charge. Are you able to convert between the units of charge? 20 NC here, that is nanocoulomb. That's again charge, right? 250 millimeters, that's distance. Okay, 300 centimeters, again, that is what? That is distance. Okay, right. The conversion of area will be done here from square centimeters to square millimeters. All right. So the expected answers there to the baseline assessment grade 12 would be to define electric field, to say it's a region of space in which an electric charge will experience a force of attraction or repulsion. So there's a region around that space. We spoke about this in grade 11. A charge would have this region, right? An invisible region. We can't actually see the electric field. It's invisible, but if you bring another charge, that charge will either be attracted or be repelled by the other charge. So that region is called the electric field. It's like that region of magnetic field. Okay, if you remember the magnets, they can attract and they can repel each other. Actually, magnets would work similar like the electric charges. Okay, so they attract or repel each other. If you bring two magnets closer to each other, you can actually feel it before they either attract and touch or they repel each other. There's a feeling that you get when you are holding both of them, as they are actually fighting to either go touch each other or they're fighting to push each other away. That is the region that we are talking about. And that region also exists with electric charges. Around them, there's a region that exists where an electric charge will experience a force of either attraction or repulsion. Okay, with the drawing of electric field between the two parallel plates, the expectation that it should look like this, they should be going from the positive plate to the negative plate. And the field lines directed from the positive plate to the negative plate, yes, if you have done that, okay, you must always make sure that the field lines are evenly spaced. Okay, you remember it was a very, very important point there that we were speaking of last year. And remember, grade 12, we don't say that just because things were done in grade 11, we leave them there. These things are still examinable even in grade 12. So we need to remember them, okay? The electric field strength is the same at all points between the plates. They actually, them being equally spaced, okay? And going from the same position here, having the same distance from here to here, that's what it is saying. The strength is the same, they are uniform. That's what we're actually saying. The electric field is uniform. Okay, right. The edges of the electric field is weaker than the non-uniform. At the edges here, it starts becoming weaker. Okay, right. Then there was a point where we were being asked to calculate the area, okay, of a shape with the length of 2 centimeters and a breadth of 4 centimeters. There, grade 12. And to calculate that, we would obviously have to know the formula for area. This is where I wanted to go. We must remember the formula for areas. For this rectangle, the formula for area is length times breadth. Okay, we must know this. And for the square, because when it comes to capacitors, these are the possible ones, okay? And this one being the most likely one to be asked. For the square will be the side square. Side square, some people say it is the length square. Whether it's length square or side square, it's the same. Just using one length that will be given to you or one side that will be given to you. Rectangle will be the most likely to be asked, okay? So we are trying to prepare ourselves just in case they don't give us the area. They actually give us the length and the breadth or the side of the square. Okay, so here we have to convert. As you can see here, where I have substituted, it has been converted. It was given as 2 centimeters, but now I've written it as 2 times 10 to the power minus 2. That's me converting from centimeters to meters. I have to convert to standard units for me to be able to calculate. Okay, and then here again the same thing has been done. I have converted from 4 centimeters to 4 times 10 to the power minus 2 meters. That's conversion from centimeters to meters. And that's the conversion factor there, times 10 to the power of a negative 2. Or some other people would divide by 100. If you divide by 100 and you are used to that, that is also fine with us. If you press that into your calculator, it should give you the answer 0.0008 meters. Square meters. There is a mistake there. Square meters is the SI unit of area. It's actually 0.0008 square meters. Shouldn't be just meters like that. Okay. And then the last one was asking us to convert 600 picocoulomb and then 20 nanocoulomb and then 250 millimeters and then 300 centimeters. Okay, so the conversion factor there will be 600 times 10 to the power minus 2. Then it will be coulombs at the end of the day now, because it has been converted. And nano, but the main point here is, are you able to convert do you remember the conversion factor of pico? The conversion factor of pico is times 10 to the power minus 12. The conversion factor of nano is times 10 to the power minus 9. The conversion factor of milli is times 10 to the power minus 3. The conversion factor of centi is times 10 to the power minus 2. This is the reason again, of why whenever I convert between these units, I always try to use times 10 to the power of something, okay, so that we can have uniformity throughout our conversions. Whether you are converting from millimeters to meters, use times 10 to the power minus something, or that's how I feel, because it will get very difficult for you to start dividing by these big numbers. If it's times 10 to the power minus 12, what number is that? It's times 10 to the power minus 9. It will get difficult for you if always you are going to divide by 1,000, by 10,000, by million. You understand? It starts getting a bit difficult. You will not forget, you will not remember 10,000, you will not remember a million. So it's easier to remember times 10 to the power something. So all of them, I just do times 10 to the power minus something. But again, this cannot be an instruction, it is just an advice. But this is how you actually convert between the units. Okay, I'm able to do this. If not, something that you need to fix as quickly as possible, because it's going to be needed not only in this topic that we're doing, in a lot of topics there, grade 12. Okay, so fix that quickly. If you are struggling with it, make sure that you are going over it and you understand how to convert between units. And if you are able to do that, then we are good to go. Let's continue with our lesson there. All right, so the terminology for today, it's not a lot. Like I said, there's a limited number of questions that even the examiner can ask here. Our terminology here would be a capacitor, which would say is a device for storing electrical charge. This is actually the definition of a capacitor, a device for storing electrical charge. Okay, and then we must know capacitance. Capacitance is the amount of charge a capacitor can store per volt. Okay, the amount of charge a capacitor can store per volt. These ones we need to know their definitions. Okay, and then we need to know the difference between the two. I want to emphasize again, a capacitor is a device. Okay, a capacitor is actually a device, but capacitance is the amount of charge that then can be stored in that device. It's the ideal capacitance. If I were to make an example of comparing the two things, it's like a resistor and resistance. Okay, I hope now you remember these ones. You are used to been doing this one since grade 8. Okay, where you are talking resistors and resistance, right? A resistor is an actual device, right? A resistor is an actual device. Then resistance, okay, is the limiting power into current, okay, by this resistor. How much does it limit the current? It's the idea, it's the concept. The concept is resistance, the device is resistor. Okay, you want to have resistance, you need a device called a resistor. It will give you resistance. Okay, you want capacitance, you need a device called a what? A capacitor. It will give you capacitance. Okay, so there's a difference between a capacitor and a capacitance. you must make sure that you understand that you cannot just confuse the two. Let us not say whenever we're asking you to define capacitance and then you say it's a device for storing. Capacitance is a concept. Capacitor is the device. Make sure that you know. Okay, right. In one of the terminologies, you would hear us using terms like a charge. Okay, no need for you to define a charge. We're not defining the charge there. Potential difference. Should have said potential difference or voltage. Some people refer to voltage. I like using potential difference, but I can also move from one to the other. So potential difference is voltage, right? Dielectric material. This one we do not need to define it, but I thought let's write what it is, since maybe for some of you it might be the first time you're encountering it. I'm pretty sure for everyone they've encountered charge before, spoken of charge, spoken of potential difference before, but dielectric material, some of you maybe it's the first time. What is a dielectric material? It is just an insulating material. It is an insulating material. Okay, so it's called a dielectric material. Then you will hear us talking a dielectric material throughout the lesson, and then maybe you'll be confused what it is. So that's part of the terminology. Okay, but not a lot of terminology there. Great talk. Okay, so let's get right into it. Capacitor. What is a capacitor? We repeat again. It is a device. There it is here. This is a capacitor. These are different types of what? Of capacitors. There's more than these. The ones that I'm showing you. I was just showing you just a picture so that you are familiar with a picture of how a capacitor looks like. For those of you who are doing electrical technology, you are more familiar with these things. You've seen and you've even touched a capacitor. It is very, very important that if you get your hands on it, touch the capacitor, see the capacitor, even use the capacitor if possible. Okay, so this is a device for storing electrical charge. What does a capacitor do? It stores. Okay, you take something, you put it there, you are storing it. You're saying, I will use it when I need it. Okay, so the capacitor is there to do that. It stores electrical charge. Rate off. So its job is to store electrical charge. What is the circuit symbol for a capacitor? This is a circuit symbol. Okay, this is a circuit symbol. If you are drawing a circuit and you want to draw a capacitor, you're not going to simply just draw these things as they are, because which one are you going to choose? Next time you are going to choose this one. Not all of us are good at drawing. I myself know I'm not good at drawing. So I want to draw a circuit and I want to include a capacitor in my circuit. My circuit is going to look like this, or my capacitor is going to look like this. Okay, different to that of a what? Of a battery. Then let's say maybe I have a light bulb here. Okay, now let me connect this to a cell so that you will see the difference. This will be the cell. Now this is different. The light bulb, the capacitor and the cell are not the same. So do not think this is a cell. A cell will have a longer line with a shorter line. You would remember, longer line being the positive terminal, the shorter line being the negative terminal. We've spoken of these ones when we were talking semiconductors back then. Surely everyone knows this by now. Okay, if you don't, if you didn't, now you know. In a cell or a battery, you're going to have a longer line. It shows the positive terminal, and a shorter line, it shows the negative terminal. In the capacitor, however, the lines are equal in length. Look at them. Those are the plates. Okay, right? The lines are equal in length. There is no shorter line and there is no longer line. Okay, so that's how a capacitor is drawn in a circuit diagram, and that is a circuit symbol of a capacitor. It is extremely important that we are aware of it. And it is also extremely important, I repeat, that at least we have seen different capacitors, at least one or two capacitors before, how they look like. And I'm pretty sure, in fact, when I say electrical technology people, I was not thinking, almost every one of us have seen these things, okay? We all grew up with this electronic material, your radio, TVs, okay? And over time, some of us have opened inside there is that green thing they call the motherboard. These people who are doing electronics, they call that the motherboard. And also the electrical technology people, they call that the motherboard. There is that motherboard thing. It has these things. You've been looking at these things and you didn't know, what is it? What are these things? These are capacitors, okay? And capacitors are rated, as you can see here. this capacitor is rated 1000 UF there. What is that UF thing? We're going to talk about that. What is it? That's microfarad. Let me just say it, okay? They are rated, okay? And then here is the 50 volts. It's rated 50 volts, 1000 microfarads. These capacitors are rated. You've seen them before. They are soldered in that motherboard. You never knew what they are. Now you know they are capacitors. And what are they used for? They are used for storing electrical charge. They are used for storing electrical charge. Okay, let's take it a step further. And now let's try and explain how actually a capacitor stores electrical charge. And then the importance of the capacitor maybe in an electric circuit. Okay, right. So here's how a capacitor will be maybe connected in an electric circuit. Here you have your cell with your positive and your negative, and there is your capacitor. See those lines there? Okay, this is your capacitor connected there, and this is your what? Your LED, or let's say it was a light bulb, for example. Okay, so this is how to be connected. Now you think to yourself, okay, I know that the battery is going to be providing the flow of electrons. Here, electrons will be providing because of the potential difference in the battery, allows the flow of electrons as they move through, giving us light here in the LED. Why do we need this thing? Okay, say now there's a disturbance. What if our circuit has a disturbance here? Let's say here there's a switch that tends to open and close every now and then. Okay, there's a switch that tends to open and close every now and then. If we do not have this capacity, every time this switch is open, there will be no light on the LED. Okay, I hope you can see that and you are moving with me. Every time this switch is open, there will be no light in the LED. Only when the switch is closed will there be light, because there will be what? A complete flow of electrons in the circuit. Okay, there will be a complete flow of electrons in the circuit. All right, but when there's a gap, there's no flow of electrons, it means then there's no light here. That's a disturbance. Okay, then capacitors are there just in case of the disturbance, at least most of the time. Okay, to say if I can put a capacitor here, then I know that charges will be moving like this. Some charges, since it is connected in parallel, you remember the parallel connection, since it is connected in parallel, some charges will come to the capacitor here. And that is when the capacitor will start storing those charges, stores those charges on it. Okay, so then now the capacitor is charged. Let's say the capacitor is fully charged. If it happens that the circuit opens here a gap on this switch that is busy, normally open, normally closed, okay, it opens a gap. Once that gap is opened, then it means the charges are no longer moving from the battery point of view, at least, right? Then the capacitor will start discharging, because in a capacitor a potential difference will be created. Okay, in a capacitor a potential difference will be created. Then that potential difference will start, or those charges will start moving from the capacitor. And even though there's a gap here, we will have a movement of charges moving from the capacitor, giving us light. Okay, right? Okay, maybe I've said a mouthful here, but you still don't understand. What is a function doing and how does it work? I'm going to use this analogy here, right? Here I have an analogy here that I want to use with you, so maybe you can understand it better in terms of this analogy. Then I'll come back to the issue of charges before people get confused. All right, so let's say, okay, let's say we are staying in a farm that is owned by a person. They own this land. You know, there are people who own land, especially in this country. This person owns this land, and in this land there is a dam, a huge dam, and the municipality, right, of this area here, the municipality of this area here, let's put the area here, gets water from the dam. This dam is owned by this person. So this person, and then they connect all the pipes, and then maybe there's a valve here. Let's say there's a valve here. Okay, connect all the pipes, and the pipes are going into this area here where everyone is. So water comes from this dam to this person. Now let's say this person is one of those cruel people, right? It's a cruel person here. This person, whenever he's angry, great talk, he will come in here and close the valve. Because it's his land, he can do that. Close the valve, and whenever he closes the valve, people cannot get water. Yeah. And when the government goes to him and say, open, he says, this is my land. I will decide when to open. This is my area. I will decide when to open and when to close. Okay? This is a problem. Okay? This is a problem because whenever this person closes here, is angry, people do not have water here. Okay? So what can we do? Then the government says, let's start thinking. Okay? It's the government. Let's hope we have a government that can think like that. How about we have a tank midway? This is what is happening here. How about we have a tank midway? Here's the dam. Okay, I didn't want to ruin this diagram here. Now I can ruin it now because now I'm speaking directly to it. Here's the dam. There is a valve here. Okay, there is a valve here, or there's a valve here that this owner of this land always closes whenever he's angry. And then the government, and here is the area. Let's say this is the area where people are. Then the government decides to say, let's put in a tank midway before it actually gets to the people. Whenever this person has opened up here, they are not angry, they are happy. We know that this tank will be full or filled into capacity. The water will be filled here. So even whenever this person comes back at night and they are angry and they say, we are going to cut off the water supply here, these people, I hope you can see their grid, are not going to feel that effect, people here. Why? Because while it is cut off here, they will be using the water that was stored. Okay? Stored. They will be using the water that was what? That was stored here. You would remember that capacitance is the what? Is the device for storing electrical charge. So while this person is closed here, these people will be using the water. They won't even see that it closed. Opens, wakes up in the morning, is happy, opens it up again, and then it fills it up to capacity. So the capacitor is there just in case of disturbance. If there are disturbance, it will discharge, as is this tank here. This tank is there if there's a disturbance here. This person closes, then the tank supplies the water to the community. And when we opens, and then the water will be refilled here. As long as, and I repeat, as long as we do not use this water, or the community does not use this water until it runs out, the community will never see that the person is busy closing and opening that water from the dam. Okay, only if they use it until it runs out, then they will have to wait again. But let's say the tank is enough to say it will last the whole night. Let's say whenever it closes at night. It's just an example there. So it will be enough to say by the morning, and then it opens it, and then it refills the tank before the community can actually even notice that there was no water during the night. That's how a capacitor actually works. It will store the charge just in case there's a disturbance from the bridge or from the cell or from the power supply. Then the capacitor will discharge, giving energy to the appliances, or even a light bulb if it was a light bulb. That's the capacitor, and that's how a capacitor works. Okay? All right. Now, let's talk about the issue of night and how long does the person closes. Okay? Now, if this person decides to say, they close for the whole night, right? And the government decides to buy a smaller tank, then that tank will run out before the whole night, meaning that the people of the community will struggle again. Yes, while he is closed, they might have water for at least 5 hours after he is closed. Okay, maybe they have water for at least 5 hours. Remember that, let's say the night is going to last a whole 12 hours. They have water for about what? 5 hours. For the remaining 7 hours, they have no water. That is if the government decides to use a smaller tank. Okay? But if the government decides to use a bigger tank, then a tank that is double the size of this one, or even triple the size, let's say triple the size, then that tank will be able to what? To carry a large amount of water. Okay? Now what am I talking about here? I want to take you to capacitance, Creator. Capacitance is then now the amount of charge a capacitor can store per volt. Okay, different capacitors will store different amount of charge, like different tanks will store different amount of water. Okay, I hope you are with me, grade 12 then. Different capacitors will store different amount of charge, like different tanks will store different amount of water. You have 500 liter tanks, they're not going to store a lot. You have 2,000 liter tanks, they are not going to. You even have 4,000 liter tanks, 10,000 liter tanks. Okay, different tanks will store different amount of liters of water. Okay, so the same thing with capacitors. Capacitors will have this thing called the capacitance. Each capacitor has its own capacitance, and the capacitance is the amount of charge that capacitor can store, the maximum amount of charge. Let's put it like that. Are we together? It stores the maximum amount of charge. Obviously, it can store less than its maximum, right? But then there's a point where it cannot store any further than that. Like this tank, my tank here, can store only water that will be enough for 5 hours. Let's say, for example, that water would be what? We're making an example, 500,000 liters. Okay, 500,000 liters will be enough for only 5 hours for the whole community out together. Then it means we need a bigger tank, a tank that will take how much? Maybe 700,000 liters. I'm just making an example. 700,000 liters. It's bigger. It means it will be able to what? To store more water there. It will store more water compared to the 500,000 liter tank. They have different sizes. Okay, they can store different amount. Let me put it like that. They will store different amount of water. The same way with the capacitors. They will store different amount of charge depending on their capacitance. How much charge they can store. It is very, very important that we are able to define capacitance, grade 12, okay? And we are able to differentiate it between from a capacitor. A capacitor is a device for storing electrical charge, but then a capacitor is the amount of charge a capacitor can store per volt. Amount of charge a capacitor can store per volt. Okay, as we continue there, grade 12, now let's look into a capacitor in detail now. Let's look it into detail now. Now we've understood what it does. It's there in case of disturbances in a circuit. It stores the charge and discharges. But now, how does it happen? How does the storing of charge happens? A capacitor will store a charge by creating electric potential difference. Okay? A capacitor will store charge by creating what? Electric potential difference. How? In the making of a capacitor, one, they take two plates, two metal plates, and then they put them like this. As you can see, these two metal plates are coming in here, right? Then these plates, as they are right now, they are neutral. It means the number of protons and the number of electrons this side are equal. The number of protons and the number of electrons this side are equal. That means there is no electric potential. Okay? There's no electric potential in these plates. Only once we connect them to a cell, like is done here. They've been connected to a cell or a battery or some sort of a power supply. Now, what is that going to do? The positive side of the cell will then start pulling the electrons from the metal surface of the capacitor, like it was the case with an electrolytic cell. Hope you remember, in an electrolytic cell, the positive electrode was pulling the electrons from the chlorine, okay, during the decomposition of copper chloride, pulling those electrons. That was the battery doing. This is what the battery is going to do as well there. The battery will pull the electrons from the positive charge, okay? Electrons so will be moving here, right? And remember, once a substance loses electrons, what does it become? It becomes positively charged. So this guy will be losing electrons and the protons will remain because the protons do not move. Then these protons will be more positive, or the plate will become more positive than negative, making the plate to become what? Positively charged. Then the electrons will be pumped on the other side from the negative terminal of the battery, pumped to the other metal. So here they were neutral, there was no electric potential at all, okay? But now, once the electrons start moving from here, going to the other side, you start getting electric potential. You will get electric potential because this side becomes positively charged and this side becomes what? Negatively charged. Now let's go back to grade 11. You remember in grade 11, you had two parallel plates and we were talking about these two parallel plates. If you connect them, they are going to be positively charged and negatively charged. And this is how it actually happens. And we say once that happens, between the two plates, there will exist a field called a what? An electric field. This electric field will help the issue of what? Of electrons moving from this side going to the what? To the other side. This electric field here. So, but let's continue here. The electrons are going to this other side, leaving this side positively charged. And here we are having more electrons coming in this side. Okay? We are having more electrons coming in this side. And this side is becoming what? Negatively charged because it's gaining more electrons than it had. Remember, it was neutral. But now it is getting the electrons coming from the battery being pumped. Other electrons are taken from this side to the battery and electrons from the battery being pumped here. This creates an electric potential difference. There is a difference in potential because while these plates were neutral like this, okay, even if you connected this, okay, connected this over maybe a bulb, across a bulb like this, these charges were never going to move, right? Because there was no electric potential difference. There was no difference between the charges. This side was neutral, it was fine, it was well. The other side was also neutral, it was fine as well. But once one side has more electrons than the other side, then immediately you connect maybe a light bulb here. Okay, now remember the electrons will continue moving. If you happen to disturb here and put in an open switch here, right? What is then now going to happen? Now we are looking in terms of the particles here. What is now going to happen is that, let's say now you have disturbed, you have opened a switch here. That means electrons are no longer being pumped by the battery side. Electrons are no longer being taken from this side. But already here, there's what? There's an electric potential difference. Why? Because here, there are more positive charges than the negative charges. Here, there are more negative charges than the positive charges. The electrons will be attracted to this side. But now they can't go this side. They can't just go from here to here, right? And that was done in on purpose, because if that was the case, then this is not going to help us anyway. Okay, I hope you can see that. Here, inside this thing, they put in a material called a dielectric material. And this dielectric material is there to insulate. It's an insulating. It is their insulating material. It is there to insulate so that electrons, whenever there is an electric potential, remember the electrons now, since they are no longer equal, remember electrons are now pumped here. We have more negative charges here. Electrons are negative, you remember? And then here we have more negative, positive charges, I mean. So electrons will now want to move from here to here. They will actually be attracted, unlike charges attract each other. So electrons will want to move from here to here. But now the issue is there is a dielectric here, a material that is insulating. And an insulating material does not allow for the flow of electric current. That means it does not allow electrons to pass through it. So electrons won't be able to pass in this way. So they will look for another way. This is where we take advantage of electricity yet again, like we were doing with a galvanic cell, grade 12. So here we say we will put our light bulb along the way, so that when these electrons are now looking for the other way to go to that other side, they will move like this. And this is how the electrons will be moving through the light bulb, giving us the electricity that we are looking for, all the way up to they come to this point. Now this is going to happen very quickly in reality, grade 12. That part, we call it discharging. That means the capacitor is discharging. During that part, or during that time, we're saying that the capacitor at that point is doing what, Christoph? Is discharging. Those electrons want to go back there. It discharges extremely quickly. Okay, so that's why it's important that here, even though there's going to be a disturbance, that disturbance must be closed after some time. If you remember, the person must wake up in the morning and open the water. That person in a farm, okay? Because if he happens to not open the water for a long period of time, then whatever has been stored here will run out, okay? So it means these electrons will run up to a point where we go back to neutral again. And if we are at neutral, then there will be no electric potential difference, okay? There will be no difference where there is more positive and there is no negative. That's what is meant by electric potential difference. There's a point where we have more negative, there's a point where we have more positive. And the negative wants to go to the positive because it is attracted and it's the electrons that are moving. So that's electric potential. So if we do not close this after some time, it will go to a point where it discharges completely and you will no longer be having electrons flowing through here and we won't be having any electric current. Are we together, Creator? I hope that we are together. So when we are zooming into the particles, that's how a capacitor actually works. Okay, so we've said a lot here. We're saying a capacitor is made up of two plates. That's a very, very important thing. And between these plates, there is this material that they put inside. Okay, and this material is called a what? A dielectric material. And a dielectric material is an insulating material. Okay, these plates cannot touch. That's another thing. They must be, they have to have a distance between the two plates so that you can even put at least a dielectric material, and a dielectric material can be air as well, great talk. Okay, can be air. We can say we have a dielectric material while we just only have air, because you remember that air there is not going to conduct electricity. Okay, so what we are saying, there must be a distance. Why is it that there must be a distance? It's for the same reasons why we are putting a dielectric. If the plates are touching each other, then they are going to start conducting. Are we together, great talk? I hope we are. If the plates are touching each other, they are going to start conducting, meaning that electrons, even though we can connect a battery, we will take electrons from this side, they will go here, and then they will just keep moving like this. Okay, keep moving all around. There will be no need for the electrons to move to the other side. Okay, yes, they might move while we have a battery, but if the battery stops working, the electron will just simply move from this point where they are more negative, to this point where there will be there is a more positive charge. They will just simply move across. This is what we do not want. We want them to find another path where they will be taken advantage of by us. Obviously, we want to use them so that they can give us electricity, so that they can maintain it. It's not even give us electricity. They can maintain this light bulb glowing while we're having this disturbance here. And once this disturbance stops, it starts charging again, pulling electrons this side, putting them on the other side, one side becoming positively charged, one side becoming negatively charged, creating an electric field in between through the dielectric material there until there's a disturbance again. Then during that disturbance, the electrons wants to go back where they are coming from, and they use an alternate pathway where they will pass through the light bulb, keeping it on for us. Okay, so here's another a diagram that shows what we are saying here. In a parallel plate capacitor, you are going to have two plates, two metal plates. One metal plate is going to be positively charged, as you can see here. One metal plate is going to be positively charged, while the other metal plate becomes what? Negatively charged. Okay, this positively charged plate is positively charged because electrons were taken here and electrons were dumped here. And by doing that, it creates an electric potential difference. And electric potential difference, what is electric potential difference? Electric potential difference is basically voltage. So whenever we do this to a capacitor, we create voltage on the capacitor. Then the capacitor will have voltage across it. It will have potential difference across it. Then it will start functioning like a cell or a battery. It's not a cell. It is not, definitely not a cell, definitely not a battery. But for some time, it can function like a cell or a battery, where you will have electrons moving from one side to the other side. So because an electric potential was created by using a what? By using a cell or by using a battery. That's capacitor and capacitance, great work. That's how a capacitor is, and that is a capacitance as well. Okay, but let's dig deeper into capacitance there, great work, before we can even go to the calculations. Now, if you are looking at this, it's made up of areas or plates here, which have a certain surface area. Okay, so as I said there, these are electrons, or these are atoms that are there in the metal where electrons are being taken. So if you are going to have a bigger plate, if you are going to have a bigger plate here, bigger, that means you are going to have more electrons that you can pull out by the battery going to the other side. So then that means you are going to create an even greater potential difference. That means you are having a what? A higher capacitance. It means you can store more charge that way. If you are storing charges on these plates, if I make the plate even larger, okay, that means I will have more charges that are going to be stored here. More charges will be stored here. So I can affect the what? The capacitance of a capacitor. And how can I affect it? By playing around the capacitor itself. As you can see here, I can play around the issue of the plate, how big or how small they are. Also, if I decrease the distance here as well, if I decrease the distance here as well, that will also affect, okay, how much charges I can actually push, because this will increase the electric field between the charge. You remember when we were talking the electric field there in grade 11, it was depending on the distance as well. Okay, it was E is equals to V over D, if you remember, potential difference over the distance. The issue of the distance, if the distance was smaller, then the electric field becomes what? Stronger, meaning that it can push more electrons while pulling them on, while they are being pulled on the other side. Okay, so that way we are able to what? To store more electric charge through the decreasing of what? Of distance. That means we are affecting the capacitance there. And another way here, even the type of material that we are putting in between these two charges, even that type of material, how it will align itself. I do not want to go too deep into this one, but the material will align itself such that it pushes more electrons out of this plate, it will repel them. Okay, so the materials that will be used, the dielectric material, it must be a material that the molecules of the materials, molecules of a material will shift, and they will shift in such a way that they will push more electrons from this plate. Because remember, from this plate, we want electrons to leave. They will push more electrons from this plate, repelling them, being repelled by the negative electrons of the material. But the negative electrons of the material will take no part, and they will not move. Those ones from the material itself will not move, okay? But they will repel the electrons from the plate, pushing them so that they move even more, okay, going in this direction. While these ones are being pumped more, because for every electron that leaves this side, an electron must enter here, so that the net charge will remain constant. The net charge between the two plates must always be constant, okay? The net charge must always be constant. So for every electron that is being pushed here, an electron is going to be what? Pushed out here, an electron will be pulled in here. Okay, I hope. Okay, and then if they don't, or I should say this, most dielectrics such as M will have a relative permittivity of what? Of 1. I just feel like I should mention this great talk. There's a relative permittivity for each dielectric material that could be used, but other dielectric material will have one that is not 1. So, but if they say it's air, or they say there's a vacuum in between, or they say nothing of the dielectric material that is there, you can always assume that the relative permittivity will be 1. But the absolute permittivity will always be 8.85. This is 8.85, not 8.88. 8.85 times 10 to the power minus 12. It's a value that you can know, grade 12, but it's a value that will always be given in your data sheet as you write your exam. So that's what E naught stands for. And A stands for the area of the plate. The area overlap in square meters, but this is the area of the plate that make up that capacitor, and it must be in square meters. That's where the issue of converting from square centimeters to square meters comes in. From square millimeters to square meters comes in. You must be able to convert between that. And then the D stands for what? The D stands for the distance between the plate. How much is the distance? These are the things that we've just mentioned there. You remember when we were looking at how we can affect the capacitance of a capacitor. We can change the area of the capacitor of the plates, make it bigger. We can decrease the distance and make the distance to be smaller between the two plates. Or we can just change the material that we are using to insulate, which is the dielectric. So this formula on its own has all of those things there. Okay, so it's important that we know how to use it. The reason why I was explaining the issue of the relative permittivity is because I know I always talk of the examination guideline, and in the examination guideline, this other formula is written like this: K and then E naught A, and then E naught, I mean A over D. And one person could be asking themselves then, how do I know which one to use, this one or this one? I'm almost 100% sure that you will always be needed to use this one, grade 12, because this one, the K, that's the one that is talking of the relative permittivity. This will mean if they are asking you to calculate the capacitance of a certain capacitor, and they want you to use the relative permittivity, they have to give it to you, the relative permittivity of the dielectric material. Let's say they decide to use glass as a dielectric material, grade 12. Then they will have to give you the relative permittivity of glass. To say the relative permittivity of glass is this much. That will always complicate the calculation. So I doubt this will be used. It's there in the examination guideline, yes, but I just want to explain that the K is talking of the relative permittivity of a dielectric material. Each dielectric material has its own relative permittivity. And A will have a relative permittivity of 1. If they say A, then the relative permittivity is 1. Then anything times 1 remains that thing. Therefore, we do not need the K in our formula. I hope you are getting what I'm saying for those of you who are confused between the two. So, but most of the time, you'll just be expected to use 1 or 2. I do not see an examiner who's going to expect us to use this formula. But if they do expect us to use this formula, they will state the relative permittivity of the dielectric material is this much. Then we will have to use it. Okay, so I was trying to make that clarity just in case 1 or 2 people out there are confused between the two formulas to say, when do we use one, when do we use the other? Most probably 99% of the time, we're going to be using this one and not this one. And if we are asked to use this one, we will have to use the what? The relative permittivity of that particular dielectric that is used. But we also have the absolute permittivity, which is 8.85 times 10 to the power minus 12 there. Okay, right. So let's quickly take an example and see how we can calculate the capacitance. This is the easy part then, grade 12. Okay, we've done maybe the difficult part, the understanding of particles and how things move. Let's look at the easy part, the calculation. The easy part all boils down into choosing of what? Choosing of the formula. You can either choose formula 1 or you can choose formula 2. So from now here, we're just looking at the easiest part here. It all bounds to that. 1 or 2. Either if you can call it like that. We have formula 1, C is equals to Q over V. Formula 2, C is equals to E naught A over D. Let's look at the question, and the question will tell us which formula I will choose. Right? The charge on the plates of a capacitor is 2 microcoulombs. The area between the plate is 1.5 millimeters and the potential difference is 10,000 volts. The dielectric material used is A. If that is the case, then it means that my relative permittivity is 1. Calculate the capacitance. Okay, so you have to check what you are given there. Okay, then you have to decide, am I using formula 1, C is equals to Q over V, 1, or am I using formula 2, C is equals to E naught A over D? What is going to tell me what is given them? Do I have a charge? I do. Do I have potential difference? Yes, I do. So it means for the potential difference, I need to use what? I need to use formula 1. Simple, I write the formula. C is equals to Q over V, where Q is 2 microcoulomb. 2 microcoulomb must be converted. That is 2 times 10 to the power negative 6. That is micro. Micro is times 10 to the power minus 6. So 2 times 10 to the power minus 6, that's the charge, all over 10,000 volts. What is the capacitance of the capacitor? You will then quickly run into your calculator. 2 times 10 to the power of a negative 6, all over 10,000. Then this should give you 2 times 10 to the power of a what? A negative 10. And we said the SI unit for a capacitance is farads, named after Michael Faraday there. Okay, right. Okay, but we did not actually establish the SI unit as we usually do. So here Q is measured in coulombs and potential difference is measured in volt. So the established SI unit would have been what? Coulomb volt. Okay, this would have been the established one, or the derived one if we were deriving the SI unit. So where does this farad comes from? It was actually named after him, like the Newtons are named like, say, Isaac Newton. So we should also know that 1 farad is equals to 1 coulomb per volt. 1 farad is equals to 1 coulomb per volt. It's a very, very important thing to know there. I just wanted to pass by that before I forget that important part. Right. Then the question continues and say, calculate the surface area of the plates of the capacitor. Calculate the surface area of the plates of this capacitor. Now they want the area. We have two formulas. Formula 1, C is equals to Q over V. Formula 2, C is equals to E naught A over D. Which formula has area here? It's obviously formula 2. Nothing can be this difficult. Like I said, once we have done the understanding of how a capacitor functions, everything else becomes easy, great off. It's the matter of just choosing the formulas if we are asked to calculate. Then we are going to say, choose this one. C is equals to E naught A over D. Very important to write the formula as it is given. Now we are being told that the area between the plate is 1.5 millimeters, okay, or square millimeters. Okay, another mistake here is 1.5 square millimeters, because this is the area between the plates. It must be in square millimeters. Okay, the potential difference is 10,000 volts, and the A is using the dielectric. So we will need the absolute permittivity there, okay, which is 8.85 times 10 to the power minus 12. This is a constant value, grade 12. It will be given in your data sheet as you write the exam. Should be given. So multiply by the area. The area between the plate is 1.5. And then we are asked to calculate we are actually asked to calculate the area. So this should be the distance. Okay, this is another mistake. This should be the distance between the plates. So we have the distance. We are asked to calculate the area. So this should be A, grade 12. Apologies for that mistake there. Over the distance between the plates. So that means this was right. We do not need the square there. The distance between the plate is 1.5, and it's in millimeters. So millimeters must be converted to meters. That times 10 to the power of what? Minus 3. Okay. Now we have two unknowns. One person can say, this A is unknown, this C is unknown. But no, this C is not actually unknown. We calculated it previously because we're still within the same capacitor. We're talking about the same capacitor. Its capacitance cannot change, okay, unless we actually change the make of the capacitor itself. Okay, so the capacitor is 2 times 10, capacitance, 2 times 10 to the power negative of negative 10. And to solve for area there, we have different ways we can do that. We can simply multiply by this, cross multiply there, or just put this into a calculator. I like the cross multiplication because I do not like pressing a calculator multiple times before I find the answer. It increases chances of making mistakes. Okay, what you do on the left, you do on the right, this will cancel this. Let me continue here. I'll be left with a number like 1.5 times 10 to the power minus 3 multiplied by 2 times 10 to the power minus 10. This is equals to 8.85 times 10 to the power minus 12 times 8. Then you divide this by 8.85 times 10 to the power minus 12, divide by 8.85 times 10 to the power minus 12. Why am I dividing? A was multiplying with the 8.85. The inverse of multiplication is division. Put that into a calculator. 1.5 times 10 to the power of a negative 3 multiplied by 2 times 10 to the power of a negative 10. Okay, then all over 8.85 times 10 to the power of a negative 12. That permittivity there. Okay, the answer that we are getting there is the area is actually 0.03 square meters. That would be the area. Okay, a lot of work was needed here. So this question here will probably be out of 4 marks because there was a lot of manipulation that we were doing there. 4, if not 5 marks for an examiner that wants to give away those marks there, but it will not be a straight 10 marks because there was some manipulation that we had to do there. Okay, right. So grade 12, let's give you 3 minutes and see if you can answer these 2 questions there. Activity, it says a certain parallel plate capacitor consists of 2 identical aluminum plates, each with an area of 2 square centimeters. The parallel plates are separated by a distance of 0.01 meter, and the type of dielectric material used is air again. Okay, take note of that. Your 3 minutes starts now. Right, Greto, welcome back. I hope you were able to do that activity, and I hope you finished it within 2 minutes actually, instead of 3 minutes, because it's simple. Okay, so the activity goes again. A certain parallel plate consists plate capacitor consists of two identical aluminum plates, each with an area of 2 square centimeters. The plates are separated by a distance of 0.001 meters. So you can see here we're given area, and then we are given distance between the plates. And the type of dielectric material used is a dielectric material, that insulating material in between. Okay. Question number 1 is asking, define the term capacitor, a device for storing electrical charge. And question number 2 is asking, calculate the capacitance of a capacitor. So to calculate, first we need to remember we have two formulas. C is equals to Q over V. C is equals to E naught A over D. This is formula number 2. Which formula are we choosing? It's always about that, grade 12. Based on what we are given, we are not given the charge, we are not given any potential difference. We are given area, we are given distance. So it is clear, or it should be clear, grade 12, that we should be going for what? Formula number 2. There is no reason whatsoever for anyone to lose marks in this equation, grade 12. So we take formula number 2. C is equals to E naught A all over D. Okay? But you then take note that our distance was 2 square centimeters, which means it must be converted, grade 12. Very, very important. And how do you convert from 2 square centimeters? We've done this before here. We're now going to say from centimeter to meter, it's times 10 to the power minus 2. So that means from square centimeter to square meter, we must also square this. So it will be times 10 to the power minus 4. We've spoken about this, and this is how we're going to convert them. So it's going to be 8.85 times 10 to the power minus 12, which is the permittivity of the dielectric, the absolute one. And then area is going to be 2 times 10 to the power minus 4. We are converting it from square centimeters to square meters there. And they said the distance was 0.001. It was already in meters. So there's no need for us to stress about that. And we quickly go straight to the formula, to the calculator, 8.85 times 10 to the power of a negative 12. And this must be multiplied by, 2 times 10 to the power of a negative 4. And a negative 4, where is the negative 4 coming from? The conversion of square centimeters to square meters. Divide by 0.001. And what do we get there? Our answer should be 1.77 times 10 to the power of a negative 12 farads. If not farads, coulomb per volt. Okay? Coulomb per volt. For those multiple choice questions where they like to throw it in there, which SI unit is equivalent to the farad, A, B, or C. Right, grade 12, let's move on. This we have talked about, but I want to emphasize on it. There are factors that can affect the capacitance of a capacitor. We spoke about that. If you make the plate to be bigger, you are affecting the surface area of the plate. And if the surface area of the plate is bigger area or bigger plates, then it means you are going to be able to do what? To store more charge. More charge will be stored here because you are now having bigger plates as compared to just smaller plates. Okay, this is what I'm comparing it to. Here, this is the amount of charge that you can store. Okay, so the capacitance can be affected by the what? By the surface area, making the plates to be bigger. The first surface area of the plate will affect. These are, we call them factors affecting the capacitance of a capacitor. You can also affect it by changing the distance of the plate. Okay, if the plates are this far apart, the electric field here is going to be weak. Okay, so the push of electrons won't be that much. But if the plates are closer to each other, you're going to have a stronger electric field between the two plates. So then you will affect the capacitance, meaning that you will be able to push more electrons on one side them going to the other side, creating that electric potential difference that we are talking about. So distance can affect the capacitance of a capacitor. And then number 3 is the type of material that you are going to use to insulate here. Your dielectric material that is used to insulate here. It can also affect if you have a material that will align itself easily and quickly by pushing and repelling the electrons on one side and then them coming on the other side, or compared to other ones. But the issue of how the type of dielectric material affect is not that important for you. You need to know this one, how it affects here. You need to know that the bigger the surface area, the greater the charge that can be stored. Okay, you need to know that the smaller the distance between the charges, the greater the charge that can be stored. But here it's not that important. But even if you wanted to know, to explain it, it's how the material will align itself such that it repels electrons on one side of the plate, and then there's electrons coming in on the other side of the plate, making this plate more positive and then the other one more negative. So that's how a dielectric works. But I don't see in the examination guideline, it does not specify that you will have to explain how a dielectric material actually affects the capacitance of a capacitor. But nonetheless, I have told you, and I hope that you understand what I have said. So those are factors that affect the capacitance of a capacitor. So that's one of the things that you can know after knowing how a capacitor functions. Okay, and then from there we should look at examples of capacitors used in technology. Okay, just a brief knowing of examples of capacitors used in technology. Okay, they are there in the examination guideline, they are listed for you there. Just know that they are used in filter circuits, in power supplies, and then also they are used in separation of frequencies between woofer, which is a bass speaker, and tweeter, which is a high pitch speaker there. So they actually filter electronic noise. So you can just say electronic noise filtering. They are used for electronic noise filtering. So instead of saying they separate the frequencies between a bass and a tweeter, you can say they are used in electronic noise filtering. So, okay, they can also be used for power factor correction. They can also be used to correct power factor there. So power factor corrections, they are also used for that. So that's where you find capacitors being used. So as to how that would need us to go into a lot of details, how they actually filter circuit and power supplies and all of that. But what I would like you to know is where they are used, so that if you are being asked to list the uses of capacitors in technology, at least you are able to do that. Okay? All right. So let's quickly look at an example of a typical previous question paper where they are asking us based on capacitors. Okay, so let's look at that and see if we can be able to answer those questions together this time around. Question 8 says 2 parallel plates A and B in the diagram below forms a capacitor. The place of a capacitor is 6 millimeters apart. You start noting there, 6 millimeters apart, with each each with an area of 0.03 square meters. Okay, luckily for this one, it's in square meters. No need for me to do what? To convert. The dielectric material between the plate is air. Okay, and then answer the following question. So as you can see here, most of the time the dielectric material that is going to be used is air. And then again, for the reason for that is so that we can have the relative permittivity of 1. Air has a relative permittivity of 1. Other materials, we don't know their relative permittivity by head, and we can't do that. And it will be difficult to have a data sheet with the relative permittivity of all types of material that can be used. So most of the time it's going to be air, or they will just simply not mention it in the question. And if they don't, you assume that it is air as well, and you continue. Right. So, right, before you can even do anything, maybe some of you would say, let's quickly convert that. 6 millimeters should be converted to meters as 6 times 10 to the power minus 3 meters, because milli is times 10 to the power minus 3. All right, and here we go there. 8.1.1 define the term capacitance. Not capacitor, but capacitance. The amount of charge a capacitor can store per unit volt. Okay, the amount of charge that can be stored per volt. The amount of charge that can be stored per volt. And then it says calculate the capacitance of the parallel plate. Now we are asked to calculate the capacitance of the parallel plate. Where do we go? Two formulas. Formula 1, C is equals to Q over V. Formula 2, C is equals to E naught A over D. This is where the importance comes in of knowing your formula correctly. But even though you don't know, you will find them, they will be there. Look, this is formula 1, and just quickly say name this formula 1 and name the other one formula 2. Then based on what you are given, then you decide whether this you are going to be using formula 1 or you are going to be using formula 2 based on what you are given. Then from what we are given here, we are given distance between the plates. Okay, they are 6 millimeters apart. We're also given the area. And where in which formula are we finding those things? In formula 2, great job. Easy as that. We have decided or we have chosen the formula to be used. So we are going to say C is equals to E naught A over D, where E naught is 8.85 times 10 to the power minus 12 multiplied by, what is the area? 0.03. No need for me to convert the area this time around because it is given in square meters over the distance, which is what? 6 times 10 to the power minus 3 or negative 3. Then go straight to my calculator. I should find the answer is 8.85 times 10 to the power of a negative 12 times 0.03 square meters all over 6 times 10 to the power of a negative 3 as we convert them. So we should get that capacitance is 4.43 times 10 to the power of a negative 11 farads as I'm trying to fit it in there. Right. So this should be the capacitance of that capacitor. Right. And then the next question Kraitov is asking us, name two factors which can influence the capacitance of a capacitor. Name two factors which can influence the capacitance of a capacitor. And those factors that you are going to name, you can say it is the surface area of the plate, okay, and then distance between the plates, okay, or the type of dielectric material used. At least they said name, but they did not ask how. They can ask you how does distance affect the capacitance of a capacitor. Then you can tell them that if you have a small distance between the two plates, then you will have a greater capacitance. And then for area, the greater the area of the plate, the greater the capacitance of the capacitor. Okay? Right. So as you can see there, this is how the questions are answered. The amount of charge capacitor can store per unit volt. Okay, as we were saying there. And capacitance, they chose the same formula as us. They had to because we were saying there we have the area given to us and the distance. And this is how we substitute, they are substituting. And as you can see here, it is also substituted in terms of times 10 to the power minus 3. But that does not mean people who are dividing by 1,000 are wrong. Okay, just this one is easier, it's uniform. You can know that every time I'm just multiplying by 10 to the power something. Okay, then the correct answer there is 4.43 times 10 to the power negative 11 farads, as we found it to be. And then the factors that can affect the capacitance of a capacitor, they said distance between the plates, yes. And then they said area of the plate, yes. Okay, but obviously another person can say also the type of dielectric material, the type of dielectric material there. Okay, so Kretov, here's another question that you can attempt. This is a typical exam question also from a previous question paper there, and even check the marks that are given there, right? It says define the term capacitance. Then again, another definition. Calculate the capacitance of a capacitor. You are choosing between formula 1, formula 2, right? the distance between the plates is now increased to 0.65 meters. How will the capacitance of the capacitor be affected? This is a nice question there. If you know the issues of affecting how the capacitor, or factors affecting the capacitance of a capacitor, then you should be able to answer that question. So attempt this question as your homework and see if you can take all the marks, because that's the aim with this topic, that everyone should take all the marks. It should be 100%. Okay, take note there. Your area is given in square centimeters there, which means there should be the issue of converting. This is why I started by reminding people of converting between units. Very, very important, and being able to calculate the area at least. Another one there, define a capacitor, 2 marks. Calculate the voltage of a battery connected to a parallel plate capacitor with the area of 2 times 10 to the power negative 4 square meters and the plate separation of 2 times 10 to the power minus 3 meters. Already converted for you. If you can see this one, it's already converted for you. If the charge stored on the plate is what? 4.0 picocoulombs. This is where now you are going to get a problem if you do not know how to convert the charges. Okay, try it again, also that one as your homework, and then let's go over our summary for our lesson there. We wanted to be able to define a capacitor, we've done that. We wanted to be able to define capacitance, we've also done that. And then we've said, are we able to calculate the capacitance of different capacitors using the potential difference and the charge? Yes, that's when we're using the formula C is equals to Q over V, which we called formula 1 for this lesson. Okay, calculate the capacitance of the capacitor using the area and the distance between the plates. That's when we're using formula 2. C is equals to E naught, which is the absolute permittivity, A, the area of the plate, over D, the distance between the plates, which are also, these two are also factors affecting the what? Also factors affecting the capacitance of the capacitor. So the factors affecting the capacitance of the capacitor, they are right there in the formula itself, grade 12. Okay, and then here we're talking about stating the factors. 2 of them are already here. Area of the plate, and then distance between the plate, and then the third one is the type of dielectric material. And we know, or we should know, how they actually affect that. Then give examples of capacitors used in technology, electronic noise filtering, power factor corrections, and then these are type of the examples that we have looked at. So we definitely did look at that as well. And then we also looked at how the capacitor actually functions, and then given even that analogy of whenever there's a disturbance, the capacitor will always be able to discharge what it has stored. And then talked about how fast it discharges, talked about that how it actually charges by electrons moving from one plate going to another plate, and then when they move this plate, it becomes positively charged, and then when they enter this other plate, it becomes negatively charged. Then there is an electric potential difference, and electric potential difference is voltage. Therefore, the plate will then start operating as a what? As a battery, or almost like a battery. If in case of a disturbance, maybe there's an open switch, the battery can no longer provide that energy. Okay, so that's how a capacitor actually functions, and I hope people are getting the function of the capacitor. Grade 12, do not forget to join us again next time on the 22nd of August, same time, 14:30 to 1600 hours. There we'll be doing electric circuits, like we said at the beginning, electrostatic and electric circuit. Actually, we try to do them together like that. So we'll do electric circuits, and then we'll look at all those Ohm's law, resistance, total resistance, current, and all of those things. So make sure to join us for that lesson, grade 12. Grade 12, let us call it a day. Thank you.